Hi, in this video you'll learn about the geometric random variable. The particular example we're looking at is the number of bit transmissions until the first error occurs. So let's look at the particular problem. The probability that a bit transmitted through a digital transmission channel is received in error is 10%. So a bit is going to be transmitted, there will either be an error or not an error. So the probability it's not transmitted in error is 90%. Assume that the transmission trials are independent. And what this means is if we transmit one bit, it's an error, it doesn't make the next one that's being transmitted more or less likely to be an error. The trials are independent. What happens in one transmission does not affect either better or worse the next transmission. So let X represent the number of bits transmitted until the first error occurs. And we want to determine the probability mass function of X. And probability mass function, what we're talking about is we want to determine the function f of X. So again, with a geometric random variable, there's a story here. X is the number of times that you do something until you get your first success. Unfortunately here, a success represents an error. And the probability of an error is 10%. There's a couple things that we need to check. First of all, for geometric, your trials have to be independent. So receiving one transmission error doesn't make it more or less likely that the next one will have a transmission error. Also, the probability stays constant. The probability of transmission error is 10%, and that doesn't change as more and more bits are transmitted. And also there's two outcomes. So every bit that's transmitted is either transmitted in error or not in error. So we've met the conditions of a geometric. Let's go ahead and model it then. So here is the probability mass function f of X. And I think for this one, it's not too bad to build this guy from scratch, so you eventually see how we get the probability mass function in a very simplistic form. But let's start out just by listing as a piecewise function, and then later we'll make it more compact. So let's just consider the case, the first support value is 1. So this is the number of bits transmitted until an error occurs. Well, it could happen on the first one, the second one, the third one. This actually, the support goes to infinity because it could be an infinite number of times, not realistically, until we actually see a transmission error. But the probability that X is 1, the first bit is transmitted in error, is 0.1. Okay, so that's a nice case. X equals 2 means that it wasn't until the second transmission that we had our first error. So that means the first one I came across was good. There was no error. Times, because I have independence, I can just multiply. The second one did come across an error, so this is 0.1. So good times bad. Okay, X equals 3. What that means is our first transmission error occurred on the third trial. So that means the first two were successful, no errors, 0.9 squared times 0.1 for the third one, meaning it came across as an error. And, well, should we build case 4? Why not? We're here. So X equals 4 means the first 3 came across well, times, and again, I'm multiplying everything because I have independence, times 0.1. The fourth one was an error, and we can go on and on and on. But I think you can see now that we can write this more compactly. So let's write this for any X instead of writing as a piecewise. So in that case, f of X is equal to, you can see what we're doing, 0.9 raised to the X minus 1 times 0.1. So this is saying the previous X minus 1 trials were successes times the last trial here was the failure or the one that was an error. And so this function is defined for X equals 1, 2, 3, and it continues on to infinity. If we actually sum this, over the support, x equals 1 to infinity, f of x, we will indeed get 1 to make it a valid probability mass function. And while we're talking about it, I think it's interesting to note this guy's expected value. We know how to find the expected value of a random variable, of a discrete random variable. We're just going to sum f of x times x from x equal 1 to infinity. And when in fact we do this, we get the outcome to be 1 over the probability of success here, which was transmitting a bit in error. So that's 1 over 10%, which turns out to be 10. So the mean of a geometric random variable is actually 1 over the probability of success. And I don't think this is too hard to see, because imagine you have a fair coin and you're going to flip it until you get your first head. On average, it will take you 2 trials. Again, it's a long run average too. If you have a die, a fair 6-sided die, on average, it will take you 6 throws until you get a 4. So here, if a transmission error occurs 10% of the time, on average, it'll take 10 trials before you see your first error. So I think that's interesting. So now we have a new random variable x. It's a geometric random variable, and let me remind you one more time of the story. It's the number of times you do something until you see your first success. Trials are independent. My probability success stays constant, and every trial has 2 outcomes. So there's the geometric, and I hope it made sense, and you can go off modeling a geometric now. Okay, we'll talk more.